far in our course, we've seen functions where a variable is part of the base, so something like x squared or x cubed. But is there a function where x is actually part of the power? So for example, if we take our original function f of x equals x squared, and I interchange the roles of the 2 and the x, so now the 2 becomes the base and the x becomes the power, is this new function that I've created, is this even a function? And if it is a function, what does it look like? What we're going to do on this slide is we're going to create a table of values to see if we can get some ordered pairs and give a rough sketch of what this relationship might look like. So I've decided to use the following numbers here, and I've used quite a few here so we can get a general sense of what it looks like. Using only 2 or 3 values may not give us a really good idea of what this relationship looks like. So beginning with -2, if we make the substitution, we get 2 to the -2, and this is the same thing as 1 over 2 squared, or 1 over 4. If we were to put in the value of -1, we get 2 to the -1, which is the same as 1/2. If we put in the value of 0, we get 2 to the 0, which is equal to 1. Putting in x equals 1, we get 2 to the 1, which is 2. Substituting in the value of 2, we get 4. And finally, substituting in the value of 3, we get 8. So if we were to plot these ordered pairs, our first one would be -2 and 1/4, which I have over here. So -2 and up 1/4, -1 up 1/2, 0 and 1, which is here, 1, 2, which is here, 2, 4, and 3, 8. And what we want to do is we want to connect these together like so. So this graph we have here gives us a rough idea of what 2 to the x looks like. So we see that over on the right side of our y-axis, we call this exponential growth, because as x gets big, this graph grows really, really quickly. And over on the left-hand side, we have kind of like a tail that drops off towards the x-axis. It's never quite going to touch the x-axis, because if we substitute in a value of x, we're always going to get a fraction that's bigger than 0. So this one's never going to touch the x-axis, but get very, very close to the x-axis as we put increasingly larger negative values inside. So often we'll say that there is a horizontal asymptote at y is equal to 0. And finally, taking a look at our graph, we can conclude that 2 to the x is a function. That's because there's only one y value associated with every single x value. Our work on the last slide leads us to the following definition of an exponential function. An exponential function with base a is given by the following representation. F of x is equal to a to the x. The domain of an exponential is all real numbers. Any value that we choose for x, we can substitute into this particular function. For the purpose of our course, we're also going to assume that a is greater than 0 and a can't be equal to 1. Now, what we might want to note here are a couple of characteristics of all exponential functions. And the first one is if we do make a substitution of x is equal to 0, we're going to get a to the 0, and that's equal to 1. So every exponential function does pass through the point 0, 1. Also, every exponential function has a horizontal asymptote at y is equal to 0. Now we can divide up our graphs into 2 different cases. There's a case when a is greater than 1, and that case I'm going to draw here in blue. So this is the general graph we get where a is greater than 1. And we also have the case where a is a fraction. In this case, we call this exponential decay. And our graph is going to look something like this. So in green here, this is for values that are between 0 and 1. So any fraction that's less than 1. Just so you can see a couple more substitutions, let's go ahead and evaluate f at 2 and f at negative 3 for the following two functions. Let's begin on the left side with f of x equals 4 to the x. First, we're going to substitute in the value of x is equal to 2, and we get 4 squared. 4 times 4 is 16. Next, let's substitute in the value x is equal to negative 3, so we get 4 to the negative 3. This is the same thing as 1 over 4 cubed. And 4 times 4 times 4 is 64, so we get a fraction 1 over 64. Over on the right-hand side, let's look at the function 1/2 all to the power of x. We can go ahead and substitute in f at 2. We're going to get 1/2 squared. This is the same thing as 1/2 times 1/2, which is going to give us a value of 1 over 4. Next, let's substitute in the x value of negative 3, so we get 1/2 to the negative 3. So we can use the trick here where we flip our fraction to get 2 over 1, and then change the negative power to a positive power. So this is really like saying 2 cubed, which is equal to the value of 8. Let's take a look at an example where we begin with our base exponential graph, 3 to the x, and we want to make some manipulations to this base graph to get a new function that we call g of x is 3 to the negative x plus 1. Now first I want to deal with the negative x. This negative x is going to cause a reflection over the y-axis. So in order to accomplish this, I'm going to leave my point 0, 1 as it is, and leave my horizontal asymptote as it is. And I'm going to take all of this information I have on the right-hand side, now it becomes the left-hand side, and then all this information on the left-hand side now becomes the right-hand side. So now we've dealt with our negative x, the next step is to look at this plus 1. And since this plus 1 is happening on the outside, this is going to result in a shift upwards of 1 unit. Now again, I'm going to focus on this point that I know and this horizontal asymptote. If I'm shifting up 1 unit, that means I'm going to add 1 to all of my y values. In particular, this point 0, 1 goes to the point 0, 2 now if we shift it up 1 unit. And also our horizontal asymptote is going to shift up 1 unit as well. And our horizontal asymptote is now going to be at y is equal to 1. And then we fill in the same rough shape that we have down here, and we get a function that looks like this. For the next couple of slides, I want us to view exponentiation in a bit of a different way than we normally do. Now I want to focus our attention right now on 2 to the x, thinking about this kind of exponential function. Now our normal number line, to move from one spot to the next spot, we do a plus 1 kind of thing. So in this case, we're going to take 0 plus 1, 1 plus 1 is 2, 2 plus 1 is 3, and this develops our usual number line under a plus 1 kind of operation. Now if we take our exponential function, which is 2 to the x, we have base 2. So we're going to take our number line and we're going to think of it in a times 2 kind of way. That means we're going to start here at 0, and each step that we do in the right direction, we're going to multiply by 2. So we have 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on and so on. Now let's say we wanted to move in a negative direction. Well, we have to do the opposite of multiplying by 2. So if we want to get from step 0 to step negative 1, we actually have to divide by 2. And if we take 1, which is in red here, and divide by 2, we get the number 1/2. If we take 1/2, and again divide by 2, we get the fraction 1/4. So you can see here that what we've done is we've developed a number line to talk about the function 2 to the x. In blue, we have multiplications by 2 as we move to the right, and divisions by 2 as we move to the left, because 2 is the base of our exponential function. So we're going to be either multiplying or dividing by certain powers of 2. Down here represents the step number, or the value of x that we have. So, for example, if I want to figure out 2 to the 5, well, I could look at our number line. We look at step 5, that's 32. That's because we've started at 1 and we've multiplied by 2 5 times. This kind of visualization also allows us to solve exponential equations. So, for example, we have 2 to the x is equal to 1 over 4, and we're trying to figure out how many steps we've taken. Well, in this case, we've gone -2 steps to get our value of 1 over 4. We've taken 1 and divided by 2 twice. So it must be that x is equal to -2 in this case. One of the nice things about seeing this visualization of the number line in a different way when thinking about exponentiation is that it allows us to see a bit clearly what it means to take a fractional power. So for example, if we think about the exponential function 16 to the x, again we're going to start at step 0 with the value of 1, and as we move to the right we could multiply by 16, and at step 1 we should have a value of 16. And moving one more step to the right, we could multiply once more by 16. 16 times 16 is 256. And of course we could do this in the reverse direction as well, so we could divide by 16 to get to step -1, and that will give us 1 over 16. And we could again divide by 16 one more time to get to step -2, and that's going to give us 1 over 256. Let's take a look at 2 fractional powers of 16. The first one is 16 to the 1 over 4, and the second one we'll look at is 16 to the 5 over 4. Now, what does this 1 over 4 really mean? Well, x, or the power, represents the number of steps that we're taking along this number line. So this is indicating that we're taking 1/4 of a step between 0 and 1. So in green here, I've divided that step from 0 to 1 into 4 pieces, and we see that if we do a multiplication of times 2 in each of these little boxes, we get an overall multiplication of 16. 2 times 2 times 2 times 2 is equal to 16. So that means at each of these little spots here along our green division, we're going to multiply by 2. So our first one is 1 times 2, and then 2 times 2, and then 4 times 2, and then 8 times 2 to get to our 16. So now we've divided 1 into 4 equal spots. We have a 1/4, a 2/4, a 3/4, and a 4/4. This expression, 16 to the 1 over 4, means find the red value up at the top where the number of steps we've taken is 1/4. Well, here's 1/4 of the way to 1, and the red number above it is the number 2. Just like the 4th root of 16 is equal to the number 2. This just gives us a different way of visualizing this relationship. Similarly, if we wanted to find 16 to the 5 over 4, this means we need to take 5 over 4 steps from 0. Well, we already have up to 3 over 4. 1 is going to be 4 over 4 steps, so we need to figure out the red number above this green hash right here. And we noted that each one of these is a multiplication by 2. So the red value that must go above here is 16 times 2, which is 32. So 16 to the 5 over 4 is 32. Much like 16 to the 5 over 4 we represented before as the 4th root of 16, and then take the power of 5. 4th root of 16 is 2, and 2 to the power of 5 is 32. So again, this just gives us a different way of visualizing the relationship between the base number and our power. All right, my little epsilons, stay positive.